Welcome everybody to the latest Trillium webinar entitled Centrifugal Pump Selection, Avoiding Common Mistakes. Just a couple of pieces of housekeeping. At any time, please feel free to ask questions. There is a Q&A box at the on the lower bar on the Zoom dialogue. You can click on that, you can type in your question. There will be time for us to answer questions at the end, but please feel free to enter your questions at any time during the webinar. The webinar will also be available on the Trillium YouTube site a couple of days from now. So if you miss anything, you can always go there to catch up on it. And with that, I think we'll kick off the webinar. So if you want to go to the next slide, please. Okay, just an introduction on who you're going to be hearing from today. So I'm Simon Bradshaw. As it says here, I look after engineering for Trillium Flow Technologies. I've been in the industry a long time, mainly because it's a lot of fun. I've done quite a bit of stuff with various companies. I'm a chartered engineer and I hold various patents and other interesting things. The two important people, the two smartest and nicest people I know are going to be doing the heavy lifting on this. One of them is Francesca Rizzi, who currently serves in product management. Product management, holds a master's degree in mechanical engineering and has 20 years of experience. And Sam Eccles, who has an engineering background primarily, 16 years in the industry, and is currently a product director for Trillium. And let's go to the next slide, please. So this slide just gives an overview of the Trillium Technology brand. We have a whole bunch of brands, some of which you'll be familiar with, that are synonymous with pump and valve industries. So on the pump side, we have Begeman, Flowway, Gabionetta, Thermomechanica, Rotajet, Wemco, and WSP. And on the valve product side, we have Atwood and Morrell, Autotorque, Batley, Blakeborough, Hopkinson's, Saracen, Sabine, and last but not least, Red Point valves. So some of these are say synonymous with their industry. So here, this just it shows the innovation that we've been in the business a long time, 190 years. Despite that, we're continuing to add new products and services to improve our customers' processes and productivity. Some recent examples are the addition of Red Point valves, which joined the Trillium family in 2020. And in 2022, we added Thermomechanica Pompe, which significantly enhanced our expertise and offerings in the power, water, oil and gas market, as well as our aftermarket services and repair portfolio. This provides an extensive network and knowledge base to support service, not just Trillium products, but also equivalent products from other OEMs. So with that, let's go to the next slide. This just shows very briefly the range that we cover, and with the exception of a few very specialty pumps, we pretty much cover everything. Those of you who are familiar with the API or HI designations will know a lot of these. We have the overhung ones in light blue, the between bearing pumps in green, and the vertically suspended pumps in gray. And on the right-hand side, it's just calling out that we tailor these pumps for the oil and gas, water and wastewater, power, and general industry markets, and the expectations of customers in those segments. So let's go to the next slide, and I'll hand it over to Sam.
Perfect. Thank you very much, Simon, and thank you everyone for your time. So today, as you've all signed up, what the main topic that we wanted to talk around is common selection mistakes. So we wanted to really just take the time to have a bit of a discussion around a very high level overview on the handover point between the purchaser and the pump vendor, and where currently we see most of the errors happening. A lot of these are the same things you would have seen if we were talking a few years ago. And as well, we also want to talk about some of the potential solutions and some of the ways that these can be resolved. Firstly, we wanted to just take some time to acknowledge why it's difficult, why any selection mistakes happen. You know, the technology is well understood, the technology is very mature, physics hasn't changed. You know, these things should be incredibly well understood, and we shouldn't, in many ways, be making a lot of the same mistakes. We're a very highly regulated industry. We work to a series of standards, whether it's HI, API, or a million and one others we could reference. So the fact that so many pumps are oversized in the field, on the face of it, can feel quite unusual and quite strange. And we want to explain why that is. And we want to split that into two camps. There's one of it's a difficult problem to solve. Obviously, we are biased, but there are no stupid people in these industries on either side of the table. And we want to make sure we understand, make it very clear that we understand how difficult the challenge is. We are not working with digital systems that are on or off. We are dealing with tolerance stacks, assumptions that have to be made, products that change, environments that change, systems that are changing their interaction all the time, and pumps that are not the same when they're installed on day one as they are when they're operating after 20 years and they're in a more worn condition. And we're all trying to make a system work that's got to operate with all those variables in play. So it's no wonder that a naturally conservative mindset kicks in, and we're going to explain some of the problems that can cause and why it's detrimental. The other side of that is there are problems that are self-generated, and those are self-generated where specifications are incorrectly applied or the wrong pump types picked. And we're going to talk through again the impact these have, why it matters, why we should all care about it, and ultimately what we can do to help correct some of these issues. Again, as Simon said, at any point, please drop the questions in. If it fits within the flow, we'll answer them there and then. If not, we'll certainly come to them all at the end. So we could have spent many hours talking about these common mistakes, but we've tried to just split it into this top handful. The number one issue that we certainly see is Capex optimization. And what we mean by that is upfront cost evaluated against everything else. And again, this happens for a reason. Budget cost is a known quantity. Comparing that to a maintenance spend or a future efficiency saving, when you're having to make assumptions on how often the pump's going to go down, what's going to happen to the system, if the system's still going to be running in 10 years, it's natural that we put more weight on what is more certain, which is how much is it going to cost me to buy. But we are going to highlight that that's not really the best way of thinking from an end user's point of view, and certainly from an overall energy consumption and efficiency point of view, as we'll walk you through. Incorrect pump type, again, this is one that's to do with very established industries, and yet there are still a lot of different pump types that people aren't aware of, and some of that is why we do sessions like this to try and raise awareness of the different types, highlight where there are areas where it's particularly confusing and complex, and how these small nuance changes can really add up and matter. Talk about NPSH margin, which is probably one of the ones where we can probably have the most influence between pump purchaser and pump OEM. This is an area where regularly excessive margins are applied that drive a suboptimal pump selection. And that does end up costing purchasers and ultimately end users a significant amount of money. Incorrect use of lube oil systems is a niche example that we'll give for BB5 units, and incorrect material selection is a very common issue that comes up that we'll discuss. And then finally, we'll spend a little bit of time talking through solutions, which is really, you'll hear us say this word a lot, but it's collaboration. It's transparent working on behalf of the end user, purchaser, and the pump OEM to have open and frank discussions as early as possible in the bidding process. And finally, it's about re-rating, retrofitting, and even changing the operating philosophy once the units are installed and up and running. For those of you that are familiar with pump curves, I apologize, but we have to assume that this is the first time that some people have seen them. So as a very quick overview, we've kept everything unitless because this is not where typically the fewer numbers are on slides, the more accessible we tend to find these are. You have flow going from zero flow, increasing to whatever units you want to imagine, and the same for head. What you have here is a representation of how much head or pressure the pump is producing in the blue line, and the gray line is the efficiency line. The key bit that we want you to think about as we're going through all of this is understanding that just the same as your car, or the same that you have a speed that you can naturally run at more efficiently, so does every pump. And that point for a pump is referred to as BEP, or best efficiency point. And we'll talk about on the next slide why that's so significant. But if you can just imagine it as these typical zones, so you have a green area where it wants to run and it's going to be at its most content. You have an area that the pump manufacturer will say, you can run here, but it's not our advised area. And outside of those is when you're typically going to really start to impact the life of the unit. and ultimately the system. So to follow on from that diagram, we'll just maybe expand a little bit more as to why it matters. Selection problems matter because they mean that the pumps end up operating away from their design condition. So we spend all the time and the R&D budget to make sure that we achieve exactly this design condition that's specified on a data sheet. But if that is not a meaningful condition and that is not reflective of reality, what ends up happening is you end up operating back here and the pump is running with significantly higher vibration. Higher vibration means bearing failures, higher vibration means seal failures, and extreme high vibration can cause damage to the pump and surrounding system. Bearing and seal failures are what drive your mean time between failure. They are what drive your servicing costs. They are what drive your overhaul costs. They are what drive your outage time. And that's why we should care about this topic. Because if we do not apply specifications correctly, we end up with pumps that are selected poorly, which is going to impact our pump reliability, which ultimately means maintenance, operating, and energy costs are all increased. Because not only is the pump going to go down more often, the pump's going to be operating well away from its peak efficiency. And you can see drops typically of 30 to 40% away from its peak efficiency when you're operating back here in this region. And all of this, as we'll get on to further on in the presentation, the energy cost is something that is consistently overlooked by purchasers. So it's something that we really want to strive to highlight in this presentation and really make a pitch of how we can do something about it together. And with that, I'll hand over to Francesca.
So thank you, Sam. So we can start with a typical refinery plant thought that includes 100 piping, elbows, filters, valves installed before the fluid enters the pump. All of them have a crucial impact on the system characteristics that must be estimated before the pump selection phase. Also, for several hundred kilometers pipeline, many assumptions are done regarding elevation, process friction losses, and so on. All these elements bring a pressure drop that requires estimation and assumptions, and that puts uncertainty. Thus, the process engineers will tend to oversize equipment as a common industrial practice, because an oversized pump can in any case work, and undersized can't. Which are the impacts of such complexity on pump selection? We can start to consider a simple piping system. We can see it on the next slide with a pipeline between a tank A and the tank B, and the pump operating to transfer fluid from A to B. The system at flow rate curve is composed by a static part related to the difference in the height of the tanks, and by a dynamic part related to pipeline length, elbows, roundness, valves, and all regulation elements that we have. And it represents the resistance encountered by the pump. So many assumptions are made to estimate system curve, and as a common industrial practice, as stalled-wide merges are taken, adopting a conservative approach, considering more safe oversizing than undersizing a pump system. So by referring again to the simple piping system, the pump curve is the head provided by the pump at a given flow. We can see the pump curve on the next slide, okay? And it is a visual representation of the pump's ability to move the fluid. A curve is usually defined for a specific operating speed and for a specific impeller diameter, unless using a variable speed device, as we will see further on. A curve is defined as stable if decreasing the flow, the head increases continuously. So there is one and only one possible head value for each flow. So the flow rate at which the two curves intersect is the working point of the system. And this means that almost all the energy used by the pump has been used to overcome all losses in the pipeline. The working point is not defined once and for all. Process parameters can change. Process can be regulated, for example, through throttle valves. being restrictive and conservative several times means over-design the system and then throttling to reduce the flow. In addition, all system components, each pipe, elbow, filter, before the pump, themselves introducing resistance, change over time, degrade for several reasons, corrosion, wear, and so on. And also process fluid environment can change. So on the next slide, we can see that both intentional process controlling, reducing the flow, and all other mentioned changes about processes and system components can result in a system curve moved on the left and an operating point away from the best efficiency point, where potentially several and severe impacts can occur. Lower efficiency, recirculation phenomena, vibration, and so temperature rising, reducing the impeller life, and low bearings and CS life. It results in increasing losses, having a head of surplus, and it implies waste of energy and system over-design. Standing above, specifications restrictions such high margins required or pure selection errors can introduce additional complexity and uncertainty. Also, the pump curve can change under the effect of any fluid temperature and consequently viscosity variation. For example, if the fluid becomes more viscous, the curve goes down, or for wear and corrosion, geometry can change and pump internal losses increase, and the curve moves also in this case. So, having detailed why it is difficult, let's go to see in details some common selection mistake. So over to you, Sam.
Perfect. Thank you, Francesca. And again, just a reminder, anyone, please do drop any questions in the Q&A and we will try and make time to cover them at the end. Okay, so we talked about underestimating the energy and operation and maintenance element. And what we want to draw your attention to, I'm not going to go through each section of this in the interest of time, but the key point I want to highlight, purchase and installation for a typical pump is really less than 20%. Less than a fifth of what we spend on the equipment is purchasing the equipment. The bit that makes up the 2/3 that we don't spend enough time talking about is energy usage and operations and maintenance. And this is where we mentioned at the start, you are trading off a known quantity against something that is fundamentally a prediction. And to do these predictions in a meaningful way, you do have to be able to estimate spare parts consumption. You have to be able to estimate the cost of energy in the future. You have to be able to accurately estimate your labor costs, your overhaul costs. You have to know how consistent your process is going to be in terms of how many hours the pump's going to be needed, but also in terms of how many stop starts are you going to have? Is the process going to change at all? Is demand going to go up? Is the pump likely to need to be re-rated so it's going to use more power? Actually, is this a startup condition and we're going to need a lower flow version later? So there's a good reason, as we mentioned, why this gets omitted. And I think while the industry is slowly changing, and industries such as RO, for example, so reverse osmosis, is much more switched on to this in terms of having it as part of the evaluation criteria, it's still relatively rare, despite what most people talk about, for the actual purchase award criteria to be on energy somewhat, but operations and maintenance is almost never a meaningful part of the buy-in evaluation. And that's because the industry is set up around EPC bidding, which drives everyone to focus very much on upfront cost. So we understand that limitation, but we just want to highlight and make sure everyone's very clear on it's a very different discussion when pump OEMs are selling straight to the end user and when they're much more focused on, I have a pump, here's the problems I've had, here's how many overhauls I've had to do, how can we change that and how can we reduce it going forward? There are many, many things that we can do, even within the current structure of EPC bidding that we have, to still drive more of the focus on this. And we'll talk about those as we go through them. So when we talk again about Capex optimization, just to give a very quick example, I'm not going to spend too much time talking about why you would have 2 and 4 pole machines in specific speed, because we would spend the full hour just on that part of the debate. But we're just to say that you have 2 options here, one that is a 2-pole machine and one that is a 4-pole machine, so it's running at half the speed. Units don't really matter for this, but you know, for the sake of transparency, 600 meters cubed, just over 2,500 US GPM, roughly 300 feet, or just under 100 meters of head. Now, what you can see here, we deliberately picked an example where the power consumed is relatively close. So you've got just a handful of kilowatts, handful of horsepower different, not particularly high power. This wouldn't be a pump that would get a particular amount of scrutiny or inspection or due diligence at the tendering stage. This is a run-of-the-mill pump. You look at any refinery, there's hundreds of these operating all around the, well, thousands of these operating all around the world. Any water treatment works will have pumps of this size, power, energy running. We're highlighting there's a very small energy efficiency difference, and we're just trying to bring that even in this case, even when we made very, very conservative estimates on how much maintenance would be needed, the slower running 4-pole pump will use less spare parts, will use less energy, and will need overhauling far less often, but will cost a little bit more. And we made some very conservative estimates based on a clean fluid, so the best possible case for operation and maintenance costs. And you still see that very quickly, 2 years in, the payback happens and the switchover, where you would have been much better off buying the slower, slightly larger 4-pole pump to start with. 9 times out of 10, you get driven on initial Capex cost and you buy the faster running 2-pole machine. Again, we're just trying to highlight that even for something where the efficiency looks quite similar and the extra 10-15% of the larger pump may seem like it's not an attractive purchase, it very quickly becomes that that's not the case. If this was on a service where there was a particularly erosive fluid or we're pumping a lot of particulates, this operation and maintenance would just pay back even quicker. And again, we're just trying to get across how significant the energy usage is in terms of the overall cost. So in terms of another example of incorrect pump type, so this is something that does get spotted a lot, and this is, you may get the impression from the chart that Simon went through at the start, you know, all these pump companies have been around for centuries. The broad pump types have been defined a very long time in standards like API and HI. They are quite a standardized industry. What's not standardized is for a given application, which pump do you pick? And this is why there is nuance within all of this that tells you there is still chance to get it wrong, despite the amount of standards, despite the amount of expertise that's out there. And some of that, as we'll talk about, is because of unintentional bias. We're going to talk about this section of the market where we're calling it a low flow, high head range. This is really the size where there's a lot of volume in the market, generally lower cost units within this tombstone and this performance envelope, but it's where they don't get a lot of scrutiny. There's a lot of volume. As an individual pump, it's not that significant. As a collection of pumps that will be on a site, it becomes hugely significant. And by overlooking all of those, they very quickly become problem pumps. And when we go out as our service group, it's very often pumps that fall into this performance window that we're being asked to troubleshoot. And when we say low flow, what we typically mean is below 440 US GPM or around 100 meters cubed, and any heads around 1,500 meters, around 5,000 feet. That's the rough ballpark we're talking here. And what we want to do is just highlight the impact for different pump type selection on maintenance, operating cost, your efficiency, and downtime. And we're going to do that just with a quick comparison chart. Obviously, this is all relative. What we want to stress here, all of these pumps have their place in the market. All of these pumps have applications where they absolutely make sense within that envelope. None of them are always the best pump. It's not a case of pick this one, it's a little bit more expensive, but it'll always work. It's a lot more nuanced than that. And it's a case of what's needed by the application, what's the end user after, and that really has to drive the selection. And what's dangerous here is every pump vendor has different strengths and weaknesses. So depending on who the purchaser, the EPC, the end user is talking to, they're naturally going to be led in a different path. And that is the same across all pump vendors. For example, we do not have a reciprocating product line. So it's going to be very unusual that we're going to recommend a reciprocating product. And that's not because we don't want to. That's just because it's not within our experience within the Trillium group. And I could go through all those product lines for our competitors. There is not one competitor that has a full suite of technology to offer for all this. And this is why when we come on to solutions, we'll talk a lot about collaboration. And that's not just collaborating with one pump OEM. It's very often saying you need to collaborate with 2 or 3 and understand where they all have their different strengths. So just very quickly within this tombstone, we'll just highlight some of the complexity. So the most common pump in the industry is an OH2. If you ask anyone to define what a typical centrifugal pump looks like, this is what they will draw. It's an end suction, top discharge, single stage impeller, overhung design with one bearing housing. Typically nothing special, moderate in terms of energy cost. It's not the most efficient, not the least. It's reasonably flexible, it's reasonably compact, very cheap to overhaul, and up front they are relatively cheap to purchase. I'm not going to go through the benefits of each one, I'll just talk about what's different compared to the OH2, which is almost the default solution. Where the OH2 runs short is really in terms of the higher head applications and the very low flows. You cannot go far back enough on the curve on a standard OH2 before you run into the vibration problems that we talked about earlier. And that's why everyone uses the Barsky type or the low flow OH2 for when it's very low flow or very high head. The big downside and the trade-off, because you might say, well, why don't you use that for the entire OH2 coverage? Firstly, they are no good at medium or high flow. And secondly, the efficiencies are genuinely appalling. You are looking at single-digit efficiencies. Now, the upside is they will operate safely, reliably at those efficiencies, and they are typically low-power machines. But again, as we were saying before, if you have a lot of these on your site, the fact that they are all low power, all low efficiency starts to add up very quickly. And it's again, as engineers, we understand the trade-offs, but it's making sure that we understand these at the right point in the purchasing cycle to be able to not lock in the wrong technology too early. Reciprocating pumps you can think of very much like a car's engine in terms of operation. They are efficient machines, they can be very flexibly packaged, their footprint can be quite compact. The real trade-offs you have are product containment is a challenge and not having leakage to atmosphere, and they do use a lot more spare parts than anything else on this list. In addition, they introduce pressure pulsations at much higher amplitudes than anything else here. That can cause problems downstream and it can cause problems for the equipment. Again, it depends on the power speeds and what you're looking at in terms of alternatives. BB3s and 5s, so for the very high heads, these are your only option, but these are the most expensive, the largest, and they cannot do the very low flows compared to the other technologies shown here. For the very aggressively high heads, you would typically look at an OH6, which is basically a single stage vertical unit with an integral gearbox. So these can spin at 20,000 RPM, incredibly high speed, often using inducers, which have their advantage and have their place. If you have a very well-defined operating range that you are not going to deviate from, you're not looking for flexibility on the product, it's going to operate at a point, start there, stay there, and not move. OH6s are a very good, very low-cost solution. When we run into trouble with these and when we see that we're replacing them for alternate technology is when you're trying to make them go outside of a narrow operating window. And that can be because the original design condition has changed just through new process requirements, or that can just be that the design condition was underestimated. And we're now in a position where very quickly these pumps, they will not last long in an upset condition before you run into trouble. They are much less robust than the other designs that are shown here. And then finally, you have the pitot tube, which is probably one of the more niche alongside the reciprocating products. And this is a unique technology to Trillium. It's something that we have thousands of installed units since 1970. So it's not a new technology, but it's one that we feel we need to do a better job of making people aware exists, because there are a lot of misconceptions about the technology into the market. The first cost is broadly in line with a recip pump. It's not as cheap as some of the other solutions. What it really does offer, service cost is very low, the flexibility is very high, so that you can operate at a wide range of duty points without increasing the load on the pump. And that is very unusual compared to any of the other pumps on that list. So if you're not sure of your process, if you don't know exactly where you're operating, if you do think there's going to be variation or the process is going to change, they are a very good option. There's a misconception on efficiency that we'll talk about on the next slide, but for within the right performance window, these are often the most efficient. And these can be 2, 3, maybe even 4 times more efficient than a Barsky or low flow OH2 in some of those conditions. Okay, so again, we'll just give one quick example here before we move on to the next common selection mistake. In the interest of time, I'm not going to spend too long on this one. It's just to say we picked a typical operating point. This is an actual sold duty condition. So this was a market competitive BB5 that we sold at 50 meters cubed, so 220 US GPM at 1,000 meters, roughly 3,300 feet. The BB5 had an efficiency around 54%. If you looked at the equivalent pitot tube pump, completely standard, unmodified, not a special one-off chasing high efficiency, it's looking at 58% efficiency. And this is doing this with multiple stages. This is doing this with a single pickup tube. So much fewer components to change. Now, this does not mean that the pitot tube pumps are a one-size-fits-all. If you have a contaminated product, they are not suitable because the pitot tube will erode very quickly and performance will drop off very quickly. What we're trying to get across is there's a lot of competing technologies for what are the same application, and they are all suitable at different times for different applications within the same head and flow requirements. Okay, I appreciate we're trying to get quite a lot into this overview, so I'm just going to very quickly touch on one more niche example, and this is, let's assume that you've gone through everything else, you've got the product specified correctly, everyone agrees it's a BB5. This is just a further example of a next level down of detail, where from one vendor to another, you may get steered within 2 different solutions within the same product line. So if we look at a BB5, for example, you can have these in 2 different configurations. So you can have them as an inline unit, and the advantage here, this is by far and away the most compact. It's the default option for most people. When most people think or present a BB5, this is what they have. There are many pump vendors that have an inline BB5 that don't have a back-to-back. And generally, all things being equal, it's the lowest cost solution. The downside you have is all the thrust is unbalanced because all the thrust is in one direction. Whereas when you look at a back-to-back BB5, you do end up having a slightly larger pump because it pushes the diameter up. It also pushes the length up, but you are in a position where the impellers are opposed to one another. So the thrust is balancing out to a large degree between the 2 sides. And that means you can often run a much smaller thrust bearing. And in certain cases, which is what I'm trying to highlight here, it means you're in a position where you can run without a lube system. So this is showing a BB5 skid with a lube system here. And if you can cut all this side off the equipment, not only does it reduce cost up front, and the lube oil sets can be $250,000, just to give an idea of how complex and expensive these systems are. The big benefit for end users is you have a much simpler system. You have less to monitor, you have less to maintain, you don't have to check lube oil line pressures, you don't have to do filter checks, you don't have to do temperature checks, you don't have a whole host of extra instrumentation, and it makes it a much simpler proposition to work with in the field. And lube oil systems absolutely have their place, and there are applications where you have no other choice. But when you can get away from it, we should be driving for the simplest solution, purely because that is in the end user's interest, and that is in all of our interest for putting reliable, simple equipment into the field when it's appropriate. Okay, it's quite a lot that we're trying to condense in. So with that, I'm going to hand back to Francesca, and I'll just give one last reminder. I think I've seen a couple of questions come in, but please do keep submitting them. Thank you.
Thank you, Sam. Another common mistake is related to net positive suction head and to NSS, suction specific speed. The NPSH available is the net positive suction head available at the pump impeller inlet, while suction specific speed is linked to impeller inlet geometry and suction characteristics. Being related to the requested NPSH, the net positive suction head required by the pump to operate without experiencing damaging cavitation, it is designed to ensure optimal reliability. In relation to our topic, the matter is key considering that several customer specifications take large and safe margins, actually through 2 ways: limiting NSS and requesting for conservative NPSH available. So most limitations are on the basis of 1980 years Hallam's study that 40 years ago observed a correlation between suction-specific speed and the failure frequency. It was highlighted that for NSS above 11,000, the failure frequency almost doubled. So NSS has been limited under 11,000 on several customer specifications, but it is necessary to contextualize. That analysis were partially misinterpreted, understanding 11,000 as a limit to a single number and not considering the actual application, operating, and so on. And in addition, since 80 years, hydraulic design and pump construction have been improved. So now a more graduated approach is possible. It has been observed that for teeny impellers with an S around 500, suction recirculation is not a problem, and acceptable and attainable performances can be obtained with NSS up to 15,000. Just to give an idea of how much amount limiting NSS blindly following a number, let's consider an OH2 overhang pump typical for refinery services. Considering 1 year of operation and the European energy cost, limiting the NSS below 11,000 results in a 4 poles machine selected, while raising this limit allows to select a 2 poles machine. The 4 pole machine is in these examples also less efficient, but it is not always so. And with a power difference of 30 kilowatt absorbed in the pump, quantified in about 60 kilo euro per year. So that's an example. We can see another possible pitfall that is related to material selection. Sometimes it has huge consequences, especially considering that purchaser is in charge for the application and specifies materials class on pump data sheet and specifications, and pump vendor is liable for pump warranty, and pump vendors are aligned to lowest cost. Just from these, we can say that collaboration is crucial. But to understand why, we can see the first example of material selection. And it is related to vacuum bottom applications, a very general case study, not strictly related to trillium pumps. Vacuum bottom pumps, pumping the heaviest material in the refinery, are challenging for many reasons. Because there are dirty viscous fluid to be very hot to be pumped, corrosive fluid, coke build-up, and due to viscous fluid losses and solids accumulations, and not so high differential pressure, low NPSH available, and there is also the need of warm-up provision and processes. Common installations for such services are, for example, 4 poles between bearings pump, 2 stages, slow running, and with double suction for stage impeller to have lower PSH required, suitable auxiliary plan, safeguard mechanical seals, while stainless steel internal part can deal with corrosive fluid. Customer specification required A8 construction, meaning the pump casing and internals were constructed from 316 austenitic stainless steel. Fault lies collectively is not challenging the material, but when cost of award is key, this is a common behavior. So the point is that API 610 for services above 370 require S4 carbon steel or S6, C6, 12% chrome steel, Nowhere A8 austenitic stainless steel is allowed, but it was forced at fit stage, and no pump vendor put himself in a negative position against the requirements. So the reason of a PI requirement is that these materials tend to have residual stress, and under thermal cycling become subject to significant mechanical loading, and dimensional changes can result. So especially with large impeller diameter and large dimensions. As a result of a not proper material selection, made worse by inadequate control of warm-up procedure, major casing distortion occurred after a short time of operation. Consequences are really impactful. Large amounts of engineering resource for the root cause countermeasure analysis, about several €100,000 to recover the components in chrome steel, and not considering plant downtime and the loss of production. Lesson learned and improvements are at site, properly following site warm-up and related procedure, and piping strain relief to reduce resulting forces on the pump. And at material selection point, rely on customer and user and equipment manufacturer subject material experts to review material of construction and to drop the possibility of single errors. Remarking that there is not the best material from the outset, let's see two additional cases. The first is the superheater pump installed in a gas processing plant in Middle East. Pumping water was requested on pump datasheet VCB and post-wheel date treatment due to the presence of hydrogen sulfide declared under a lovable percentage for such material. But early corrosion occurred, and hydrogen sulfide was more than the amount indicated on the pump datasheet. So the heat treatment effect was not enough, and corrosion started. This phenomenon caused pump shutdown and additional costs for downtime, reorders, and maintenance that could have been avoided spending more at the initial stage, but properly selecting, in this case, austenitic stainless steel A8 with high corrosion resistance and toughness, as done to solve the issue already occurred. The last example is related to vertical VS4 pump, pumping water, specification required, in this case, carbon steel S5+. Operating at site, corrosion occurred, and analyzing the issue, we discovered that pumped fluid was water plus something different, not declared on pump datasheet at pump selection stage. So clearly corrosive for the pump. Parts in contact with the fluid were replaced by A8, high corrosion resistant, as told, and in this case, the most suitable for the service. So our overview on the major common pump selection mistakes has already opened a glimpse to the possible solutions. Up front, grouping them, we have understood that crucial are understanding actual need and looking for alternative selection, aligning on what we are optimizing for. And then avoiding to following specification blindly and understand when to deviate. This is supported also by the examples where we have seen that there isn't the best solution from the outset, the best material, the best pump model, the best lubrication. And crucial are also transparency, openness, and collaboration within customer and user and pump vendor, relying on their respective subject material experts. On the other hand, considering pump and system interaction characteristics and several possible mistakes in pump selection we discussed about, there are some key points to prevent or to deal carefully. So we can speak about and detailed on the next slide, excessive margins at the selection stage that are to be avoided. We have to pay attention implementing solutions that are performance sensitive, such induced as variable frequency drivers that improve process control and system reliability, but at cost and resonance condition. And first of all, remind collaboration and transparency at the selection stage are really crucial. This approach is fundamental, also looking after commissioning. And on the next slide, we have details about the after commissioning. When pumps are already installed, basically we have three options. Once the system is properly analyzed, change pump speed or rerating, practically change some of the hydraulic components of the pump so that curves can change. Replace the pump or parts as cartridge replacement as in the right picture, or manage the operation through recirculation and throttling. So focusing on option one, there are two possible solutions. Varying change pump speed requires additional equipment, variable speed or frequency drivers or hydraulic couplings, and the system require system modification. And in this manner, it is possible moving the pump curves so to intersect the system curve closer to the required flow rate without changes in the pump hydraulic. The blue curves on the both head and power chart shown these at different speeds. Advantages are flexibility of operation and having pump operating point close to best efficiency point at all speeds. And also reducing peaks in starting motor absorbed current, having so smooth system transient, minimizing the risk of heavy pressure peaks within the line or sudden valves opening or closing. These advantages are for sure cost and the complexity in the system. The second option is the changing operating point by rerating. It implies the modifying hydraulic components, impeller diameter or diffuser or volutes. Here we can see an example of pump internal increased area whose consequences on the pump curve is moving the curve right and so increasing the pump flow at the same head. On the next slide, we can see some examples of rerating. The first is a vertical pump reballing. Here, the casing and the impeller were replaced by new ones designed to best fit a specific operating condition without any change in the remaining part of the pump. On the right, we can see another similar option available, especially for minor correction, consisting in trimming the impeller and reducing its outer diameter, and therefore reducing any surplus of air provided by the pump. Advantage in this case is that it is simple but extremely effective, considering that absorbed power is, as force approximation, proportional to the cube of impeller diameter. The last case that we consider is related to 6 vertical BS1 cooling water pumps installed in a combined cycle power plant in the UK. Operating flow rate requested by the system is less than those requested at the design stage. So throttling valves regulated the flow, decreasing it. The consequences of this operation were running away from the best efficiency point and recirculation effects and so impellers damaging. The solution implemented to solve this issue were focused on trimming the existing impellers and hardened them by metal coating, allowing to reach in this manner over 10% power reduction with respect to the original design. So, remembering that you can ask any question through the webinar chat box, I give the floor to Sam for conclusions and recap.
Perfect. Thank you very much, Francesca. And I appreciate that we've had a few questions in already. But as Francesca's mentioned, we're coming up towards the end of the time on the hour. So I'll keep the recap brief and we'll try and tick off some of those questions before we get wrapped up. Okay, so just a very, very quick recap. It's just the one slide on this. So it's just to highlight pumps are a slave to the system. The two are completely linked to one another. You cannot, to have an effective solution, you cannot consider either one in isolation. And that's where the challenge comes in this. You're trying to predict things with a huge amount of uncertainty and a huge amount of assumptions. And the bit that's important is collaborating together, working transparently, making sure that we understand all the technology options available in the market, applying the right ones for the right applications. There is no shortcut to that. That does require open, transparent discussion. And the real key bit that we need to work on together as a group is how do we make sure that we're applying specifications correctly and we're not particularly adding in excess margins on things like NSS limits or even suction pressures. So in terms of upfront solutions, we've covered all those in the past comments. It is just working together as a team to come up with the best solutions. In terms of installs, for units that are already operating, there are almost no limit to things that we can do to modify existing units in the field. Francesca did a great job of highlighting some of the key changes, but we could have talked for another 2 or 3 hours about different solutions that we can do. We didn't even get into how do you handle it when there's multiple pumps running? How do you change operating procedures for an existing unit without any mechanical changes? We didn't get into instrumentation, monitoring, controlling, and how we can improve reliability that way. So the key point to get away from this, hopefully, is devil's in the detail. It's all about having a partnership and lots of transparent conversation. And should you want to go into any more depth on any of the topics we've discovered, we'll send out the links to this webinar, and there are further links to different topics that we've done on, particularly on low flow, high head applications, and particularly on re-rates for units already in the field. But obviously, in addition to that, please reach out at any time. You can contact myself, Simon, Francesca via our LinkedIn pages, or you can send any questions in to info@trilliumflow.com. We really do appreciate you taking the time to join us. And we just want to take the last few minutes to go through any questions you might have. So Simon, I'll hand back to you, as I believe you have the question list up.
Yeah, so thanks, Sam and Francesca. So let's see, we have a few questions here. Let's kind of hit them quickly. Are Trillium services dedicated purely to their own products, or can they support end users in detecting any mismatch of pump rated conditions with process requirements? Who wants to take that one?
I'll let you have the first one, if that's okay, Francesca.
Thanks. Thanks for the question. Of course, not Trillium services aren't dedicated to Trillium product only, but thanks to our Sentinel experience as original equipment manufacturer, we can serve all type of pumps, and thanks to our expertise in services, we do not only serve pumps, but also machinery such as turbines, valves, gears, compressors. And our field service teams are available to visit the site and cooperate along with end users to identify improvement opportunities such as hydraulic retrofit, rerating, monitoring, troubleshooting, and so on. Okay, great. So next question. When there is uncertainty in the operating point, is it better to select a pump operating to the left or right of BEP? Who wants to take that one?
I'll take a swing at that one, Simon, and feel free to chip in. Yeah. So the answer to these is always the same, and unfortunately, it depends. Now, there's a reason that we highlighted earlier on that most pumps are oversized. There's huge caveats to this answer, but it is broadly safer to oversize a pump than to undersize a pump. As Francesca mentioned, if you undersize the pump, if you're operating probably 30% past BEP, outside of the problems you would have on vibration and NPSH and everything else, there'll very quickly come a point where your motor will not be able to turn the unit. If you were to do the opposite of that and you were to oversize the pump and motor and you're operating 30 or 40% to the left of BEP, the pump, with a few caveats, will run. And yes, you will have increased vibration, worse lifespan, but the equipment will fundamentally work. So I suppose by that definition, it's normally better to operate to the left, but that comes with more caveats than I can get in the next half hour, because it depends how many units you've got operating. Is it a stable curve? Which fluid are you on? And a million and one other factors. Simon, do you want to add any other remarks?
Yeah, I mean it's complicated, right? The what I will say is, I mean, there are generalized selection rules out there with HI, with API. In my view, they're somewhat flawed because they don't consider, for example, how much the impeller is trimmed, and I think that's not a good thing. But we could talk about this one topic, as Sam said, for like another hour. And all I would encourage people to do is I have a number of articles on this on my LinkedIn page. You may want to have a look at those, and if they don't satisfy your curiosity, then send me a message and we'll kind of talk about it. Okay, so next question we have. I'm not exactly sure how the intent here, but I'll read it out. Is there a requirement on the lowest set point for a VFD? I presume that's set point in speed. The question isn't entirely clear from the question. Does anyone want to take that one?
Yeah, so assuming that speed, the answer is yes. And exactly what that lowest point will depend on. Okay, yes, thank you for clarifying, Samuel. So yes, you just come back in terms of speed. Short answer is yes. The detailed answer, again, is it depends, but it depends on exactly which equipment we're talking about, which VFD. There will be limits of to how much turn down, so how slowly you can run the VFD based on the VFD and motor manufacturer. There will also be limits from the pump side, and that's less critical on small single stage units, but as you get into flexible rotor multi-stage pumps, this becomes very significant. And we could talk to you for another 2 hours till you fell asleep about lockout zones and resonance ranges that you will run into. There's also an element of support that the pump needs to operate well, and at very low speeds that just doesn't happen. So yes, there are minimum speeds that we need to enforce, and sometimes that's governed by the pump vendor, sometimes that's by the motor and VFD supplier. Anything you want to add, Simon?
Yeah, I mean, if you're talking about a single stage pump with an uncomplicated seal plan, the simplest case that Sam was talking about, you can probably turn down to 10% of speed. Most VFDs will let you go down there most of the time. When you're talking about a multi-stage pump, you're talking about a seal plan that has something like a pumping ring. You're talking about rotor dynamics and considerations around that. Yeah, your turn down is going to be much less. If you put me on the spot and said a rule of thumb, probably you can turn down to maybe 30 to 40% of your max of your normal speed. And I'm assuming here that we're running at 2-pole speed in the case of these multi-stage machines. So that's where I'd put it if you press me on a single figure. And then you can tell me I'm wrong later. Thank you everyone for your taking the time to attend. We really appreciate it. Thank you to the presenters, Francesca and Sam. As we said at the beginning, the webinar will be on the Trillium Flow Technologies YouTube channel within a day or two. So please look out for it there, along with all the other webinars that Sam showed on the presentation at the end there. So thank you very much for your attendance. Thank you.
Thank you for your time, everyone. Much appreciated.
Thank you.